everyone, and welcome to another two-dimensional kinematics problem. This time, the first example for projectile motion. So, a tiger leaps horizontally from a 7.5 meter high rock with a speed of 4.5 meters per second. How far from the base of the rock will she land? So, first thing I'm going to do, as with any physics problem, you want to draw a picture. And keep it simple. Don't overcomplicate it. I'm no artist, as you will clearly see. So this is going to be my tiger. Okay, so even this is probably too much artistic flair there. So this tiger is jumping off a cliff. Now we have to first finish, develop a direction system here. What directions are positive? We're dealing in two dimensions here, so you know what? Because the motion of the tiger is going forward and down, I'm going to let forward and down be positive. Okay, so I'm just going to put that down here. Forward and down are positive. Therefore, if the tiger was to go left or up, that would be negative. Okay, now, initial speed at this point, we know is given to be 4.5 meters per second. And the thing is, it says leaps horizontally. Whenever you see that, leaps horizontally implies that, you know what, it's only going in the x direction. So, we're going to say that the initial speed, which is v0 in the x direction, is equal to 4.5 meters per second. Now, something else you know in the x direction is the acceleration. Okay. For projectile motion, the case is always that the acceleration in the x direction is 0. Okay. Why? Because projectile motion means an object that is only under the influence of gravity. Okay, now for the y direction. Okay, so we're dealing with a couple things here. Assuming that it starts at this height, we're going to let that height be y0, which is going to be called 0 meters. And the tiger is leaping down, and it's going to end up at this y height. We will call that y. And we know that's 7.5 meters, since that is the height of the rock. Now, something we forgot to add in terms of the x direction is that when the tiger leaps, it's going to end up down here somewhere. So what we're looking for is this distance, this delta x, right? How far from the base of the rock will she land? Okay, so that's what we're trying to find. Now, one more thing we're actually given in the y direction, so let's just go back to that for a sec. Because the initial speed is purely in the x direction, that means the initial speed in the y direction, so Vy0 or Vy0 is actually 0 meters per second. And it's actually really important to notice that and write that in. Okay. Last thing in the y direction is the acceleration. Acceleration in the y direction is always the acceleration due to gravity. And in this case, because we let down be positive, we're not going to say it's negative 9.8 meters per second squared. It's positive 9.8 meters per second squared. Okay, so that covers us for all our knowns, our unknowns. And we're going to just hop right in. So we are looking for this delta x, right? And because the speed in the x direction doesn't change due to acceleration in the x direction being 0, we can simply solve this using this formula. Speed is equal to distance over time, right? Vx. And the key here is this Vx is the same thing as Vx0. Since, let me just shift that up, since acceleration in the x is 0. That means Vx at any time is equal to the initial speed of Vx0, which is 4.5 meters per second. So, here's the thing. So, Vx we have, and t we don't have. Delta x is what we're looking for. So we need to find time. Now, you'll notice in the picture that we wrote down a lot of different labels. Y height, y acceleration, x acceleration, y velocity, x velocity. But you know what? There's one quantity that's common to both the x and y direction, and that is time. So generally how these problems work is that you find the time using one direction, in this case the y direction, and you plug it in to the other direction, the x, in order to find your answer. So that's exactly what we're going to do. We're going to work with the y direction first, anyways. Okay, so here we go. Y direction. We're going to go ahead and use this kinematics formula since we know everything in here except for one variable. So y equals y naught plus v y naught times time plus 1/2 acceleration in the y times squared. This is our standard kinematics formula. I've only adapted it to reflect the y direction. Okay, so the displacements are in the y, accelerations in the y, speeds in the y, initial speed. Okay, now plug it in. Our y value is 7.5. The reason, again, it's positive is because relative to 0, it's down, and down is positive. So 7.5 meters. Y naught is 0. Okay, 0 meters. Vy naught is 0. Okay, so you know what? Because this is 0, this entire expression actually just disappears. So plus 0 plus 1/2 times acceleration in the y, 9.8 meters per second squared, times time squared. All right, so this is just a 0 there in the beginning. So we're left with 7.5 meters equals half of 9.8 is 4.9, keeping the units, meters per second squared, t squared. Now, in order to get t squared by itself, right now it's being multiplied by 4.9, so we have to divide both sides by 4.9 meters per second squared to get it by itself. And if you do that, you're going to cancel out everything on the right, and on the left, 7.5 meters over 4.9 meters per second squared. If you're looking at the units, meters cancels with meters, and the 1 over second squared in the denominator brings the second squared to the numerator, leaving you with, and I'm going to bring the t squared over here, t squared is equal to 1.5306 seconds squared. In order to get t squared on its own, you take the square root of both sides. See, that'll handle the s squared there for you, and you end up with time is equal to 1.2372 seconds. Okay, and again, that time is common to both directions, right? Because time does not work in just one plane. So let's go ahead and plug that in here. Now, since we're looking for delta x, let's go ahead and plug this in first, and then we'll move the stuff around after. Okay, so to pick up where we left off, we had Vx is equal to delta x over t, and we just determined that the time is 1.2372 seconds. So Vx is the same initial speed, so 4.5 meters per second. That's equal to delta x, what we're trying to find, divided by 1.2372 seconds. Now, because we're trying to isolate delta x, right now it's being divided by 1.2372 seconds. So that means we have to multiply both sides by 1.2372 seconds. Essentially what happens is you're cross multiplying, okay? So delta x is equal to 4.5 meters per second times 1.2372 seconds. And just as a check to see your units, the seconds in the numerator here cancels with the seconds in the denominator, leaving you with meters, which is in fact a unit for distance. Okay. When you multiply these two values together, you are going to end up with, let me move this up, 5.5673 meters. Okay, so that is how far the tiger will land from the base of the rock. Now, one more step, as we're used to, we have to accommodate for sig figs, right? So let's see, in our question, 7.5 meters, significant digit quote of 2. Let me just move that up a bit. 4.5 meters per second, sig fig count of 2. So we have 2 sig figs we're dealing with here. Therefore, this answer must also have 2 sig figs. So that means we're going to only have 2 decimal places, well, 1 decimal place rather, but the 6 rounds this 5 up. So in fact, delta x is going to equal 5.6 meters. So therefore, the tiger lands 5.6 meters from the base of the rock. And that is it, guys, for this video. Thank you so much for watching. I hope you enjoyed it. If you did, please click that like button and subscribe to this channel so you can see much more physics videos as they come up. Thank you, guys, and enjoy the rest of your day.